Hello, everybody. So this is going to be posted in the week 3 lecture 1 here. And so what we're going to be doing is just trying to go over some of the zyBook stuff that you should have been already doing, but maybe you weren't, or maybe you wanted some help. So we'll just jump into it. So up here where it says first zyBook assignments, we have links to chapter 1 and chapter 2. So we'll head over here. A bit slow. All right. And so in this first one, you just want to read this and mark the boxes, I guess, in the exercises. It's pretty straightforward. There's no real work on this, right? So they're just talking about history of computers and stuff like that. And you can click the boxes and get the points. Not a lot to do there. And you can see things that are maybe interesting, like the Cray supercomputer. Cray supercomputers always had this kind of form where it's like a tall part, and then it looks like a bench to sit on down there. Kind of interesting looking. Those were the most popular supercomputers back in the day. Although, of course, your laptop or even your phone might might outperform them nowadays. Um, they talk about embedded computers. Now, regarding embedded computers like this thermostat here, um, this kind of device is going to be using a CPU, probably quite similar to what we have in the Arduinos. So, when we started using the Arduinos for lecture, or sorry, for the lab, we learned that they're very slow. They were something like 14 megahertz processors, and they are very slow. But not everything needs a fast processor, and so something like a thermostat to control the temperature in your house. Doesn't need a fast processor, right? You need to be able to press buttons and keep track of what temperature it should be. You also need to be able to turn on and turn off the air conditioner or the heater as required. And so all you need is a CPU and then a way to turn on and off the heater and the air conditioner, right? I guess you also need a way for the little computer needs to be able to um, learn the temperature as well. Now, I bet that if we go over to Amazon here and we look some stuff up, um, I bet you could find like Arduino temperature sensor. You could actually get a thermometer that you could plug into um, or hook up to an Arduino. So if you think about it, we're going to be using an LCD screen, like an LCD, like 128. Well, we're not going to use the 128 by 64. We're going to use a 20 by 4 or 16 by 4 maybe LCD screen. 16 by 2 is what we're using. Never mind. I don't know what I'm talking about. But you know, you could talk to an LCD screen like this with an Arduino, and you can attach a temperature sensor to an Arduino, and we can output signals from the pins to various things that could be used to turn on and off a heater, or to turn on and off a fan, or to turn on and off an air conditioner. And so if you think about it, you probably could build uh, you probably could build a thermostat that does all the functions that you would want from an Arduino. And so it's not really a surprise that a device like this has a little microcontroller. It's what they call the tiny CPUs that they use. They generally are referred to as microcontrollers. Um, that's all you would need. So essentially, this is a lot like an Arduino, just in a thermostat form factor. So let's see, a home computer. What kind of computer is that? Well, that's just a PC, right? A home computer is a PC. A computer in an Amazon building accessed by thousands of people. So that would be a server, right? A computer in a cardiac pacemaker, that'd be an embedded computer, right? Kind of like the thermostat. A computer in a federal laboratory, that would be a server. Um, so, this is just kind of vocabulary. Cloud computing, right? That's just really doing your computing on somebody else's computer instead of your own. Um, see, post PC. We can read that up above, but we can just guess. Post PC refers to today's situation of today's most widely used computers being things other than PCs. I guess so. The number of PCs sold annually continues to increase at a dramatic rate. Interesting question. They are selling more computers every year, but I don't know if that's a dramatic rate. The PC level sales have leveled off. A smartphone isn't actually a computer. What? Of course it is. Cloud computing involves thousands of servers. Yeah. Software as a service refers to installing large software applications on a PC. No, that's not. Software as a service means like, um, web applications, basically. In 2012, about 600 million smartphones were sold. I have no idea. Let's say yes. Okay. So we can go through these and I'm just going to let you. You can do that on your own. But we do get into some later stuff here that involves, kind of prefixes and math and that kind of thing. So I want to open my notes, which says I'll be back, but I won't be back. Make the font smaller. I'll type in here if I need to type. So these prefixes, nobody uses these correctly, I think, by the way. So um, you know that there's prefixes that you have for like kilograms, um, that kind of thing, like kilograms, milligrams, things like that. Those are all the ones that are listed over here: kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, etc. And those are all technically base 10 measurements. So like a kilobyte is 1,000. And there's this other one like kibibyte, and they got an extra I in there, right? And so you can recognize these by the extra I, and the ones with the extra I are base 2. And so because they're base 2, that means they're 2 to some power. They're not going to be exactly equal to, let's say, 1,000. So what these measurements are over here are basically the ones that are closest to this. So like the closest thing to 1,000 you can get out of a power of 2 is 2 to the 10th, which is 1,024. And the closest you can get to a thousand or to a million, which is what a megabyte is, um, would be, well, 2 to the 20, which is going to be, you can grab a calculator and see what it is. 2 to the 20. Um, it's actually more than a million. It's 1,048,000, which that's why it says here, it says percent larger, 5. That's because, this is about 5%, 4.8% larger than a million. So this one over here is a million. This one over here, 2 to the 20th, is actually bigger than a million by 4.8%, which they're rounding to 5. And so these base 2 prefixes are all larger than the equivalent base 10 prefixes that you have over here on the left. And, they use that against you when you're buying things like hard drives, because, you would hope that, if you're getting like a gigabyte, you would hope that it was 2 to the 30th. You would hope if you were buying a terabyte that it was 2 to the 40th, but you don't get 2 to the 40th, you get 1,000 to the fourth. So when you buy the hard drive, it says, 4 terabytes because they're measuring this way. And then when you format the hard drive on your computer, you get like 10% less capacity because your computer measures it this way. And so there's these prefixes that are base 10 and the prefixes that are base 2. And you should just kind of be aware that those exist. Although people don't generally make it, no, they don't really differentiate in real life. So I think we're just typing here. The question is, how do they want us to type this? So like it says a terabyte is one, oh, terabyte is trillion. I think they want the word trillion, trillion bytes. Yeah. And so that's 1,000 to the fourth. Says 1,000 to the fifth is a petabyte, petabyte. A a gibby byte, I don't even know, is close but not equal to a gigabyte. So the prefixes mostly have the similar names but not identical, right? So like kilo, kibby, mega, maybe, maybe. Is it a byte? Maybe. Gigabyte, terabyte, tebibyte, etc. These nobody ever says these out loud. All right. Next section. So again, this is kind of history of computing. This stuff is just mostly in its own chapter here to give you something to do while you guys were acquiring access to the zyBooks. So we can read through this and see what kind of ideas they're talking about. So like using abstraction to simplify design. Um, yeah, I mean, everything is presented to you in a simpler to understand format, right? Like even this web page here, right? You don't have to know anything about how a computer works in order to access this web page, right? So they're giving us simple things like buttons and pictures and words in order to interact with the computer rather than kind of complicated internal um, mechanisms, right? You don't have to write code to use a computer. And so we're using abstractions. Um, make the common case fast. Yeah, that's just an idea when you're doing programming that you don't you have a limited amount of effort that you can apply, right? You have a limited amount of time and resources available. And so um, it's generally good advice to like if you're going to optimize your software and make it run faster, what case do you want to optimize for, right? Like where do you want to devote your time and effort? And so you really should be applying your resources and effort to make the most common thing fast, right? That's going to save you the most overall time. Um, so just a good idea. Performance via parallelism. Parallelism. Every computer has a lot of processors now. I'm using this is a Mac, which has an Apple Silicon M3 Max. I think I have 16 cores, although they're not all the same performance. And so if you want software to run fast, we need to figure out a way to use all those processors, right? And even if you don't have a 16 core processor, you might have an 8 core processor, you might have a 4 core processor. You probably don't have a 2 core processor. Even a lot of phones have, 6 cores, 8 cores, 10 cores, 12 cores in a phone nowadays. So you have a lot of CPUs. And so those CPUs can execute things in parallel, each CPU um, executing its own instructions. Pipelining. Pipelining is a very important concept. They'll probably talk about it more, but I kind of want to spend a minute to talk about it now just because it's interesting. So imagine you have this, right? So imagine a CPU, okay? And the CPU needs to process an instruction to execute one instruction. Like there's parts to it, right? So like the first thing you might have to do is fetch the instruction from memory. And then maybe after you fetch it, you have to decode it. And then after you do that, you might have to, I don't want to make too many steps here, but I was going to say you might have to fetch data from memory, but let's just pretend You don't have to do that. Let's just say we can execute the instruction now. So perform the computation. After you perform the computation, we might have to put the result, like store the result in memory. Something like this, right? And so um, the thing about this is, suppose your CPU takes, um, suppose this CPU could do this, you know, like a million. I don't want to say a million. I'll say suppose that your CPU could do this 1 trillion times per second, right? Suppose your CPU can do steps 1 to 4, um, 1, I want a comma there so it visually separates it, 1 billion times per second. Okay, so 1 billion times. I did 1 billion because that's 1 gigahertz. Um, right, because 1 megahertz is 1 million per second, and then 1 gigahertz is 1 billion per second. Um, so if you can do uh 1 billion times per second, you can perform these 4 steps, then your CPU will be able to run at 1 gigahertz, right? And perform, well, I guess 1 billion instructions per second. Okay. Now imagine a different CPU. Make this smaller. So we want to imagine a second CPU that works slightly differently. So it still has to do these same steps. It still does these same steps. Okay. But here's the difference. Um, the thing here is like after you fetch the instruction, then you decode the instruction, okay? But when you're decoding the instruction, the hardware that fetches the instruction is just sitting there doing nothing. And then after you decode the instruction, you perform the computation, right? Like let's say you're adding two numbers or something, that's the instruction. Well, while you're adding the two numbers, the fetching the instruction and decoding the instruction, those pieces of hardware are doing nothing. Um, and then after you perform the computation and you're going to store the result in memory, while you're storing the result in memory, you're not fetching an instruction, you're not decoding an instruction, you're not performing a computation, and you're not storing the result in memory, right? So what's happening here is that like if you say instruction number 1 here, what happens is you have instruction number 1 in step 1, and then you have instruction number 1 in step 2, and then after that, you have instruction number 1 in step 3, and then after that, you have instruction number 1 in step 4, and then after you do all that, you go back and you do it again, but now for the next instruction. So you have instruction 2 there, and then there, and then there, and then there. So instruction 1 goes through all these steps, then instruction 2 goes through all these steps, and then instruction 3 goes through all these steps. And so what pipelining does is this. So what pipelining does is first you have instruction 1 here doing the fetch. After instruction 1 does the fetch step, then instruction 1 moves on here. But while the instruction 1 is decoding, we could have another instruction being fetched. right? So both of these are happening at the same time. And then after the decode is done, then maybe we perform the instruction. But if we're performing the instruction, then now the decode is free. So instruction 2 can move there, and then instruction 3 can move here. And then after this is done, then instruction 1 can move on to the next step. And then instruction 2 can move on to the next step. And then instruction 3 can move on to the next step. And then instruction 4 can be moving here. So what happens here is that you can have 4 separate instructions. One can be on each step at the same time. Okay, so the second CPU does these steps, but the big difference, while one instruction is, at a specific step, another instruction can be doing the other steps. So overall, you could have, in this case, 4 instructions going at the same time. What does that get you? Well, it still takes one instruction the same amount of time to go through the entire process. So each one takes the same amount of time to complete all 4 steps. That doesn't change, right? So like if we said that this entire thing could take a billion times per second, right? Then, maybe this takes 250 mil, like, um, well, I don't, numbers are hard. Let's say this takes a quarter of the time. So however long it takes to do something, this takes a quarter of the time, this takes a quarter of the time, this takes a quarter of the time, this takes a quarter of the time. And when it's all done, it adds up to however much time it takes so that it could do a billion in a second. Okay. Now, when you're doing this, each instruction still has to go through all 4 steps. So each instruction still takes the same amount of time to complete all 4 steps. The difference is, the big difference is um, we have to wait through for all 4 steps up here to go through to have one instruction finished. And then you have to wait for all 4 steps to happen, and then all 4 steps to happen, and all 4 steps to happen. So it takes 4 steps. So you get one instruction finished every 4 steps here. When you're doing this, where the instruction, one instruction is on this step while another instruction is on the previous step, and another instruction is on the previous step, and another instruction is at the previous step. The result of that is that on average, um, the instructions are processed 4 times as fast, essentially. So we have one instruction finishing in each, I'm going to say clock cycle here. We haven't used that language before in this, but like let's say each of these takes 1 clock cycle, then we could have one finishing every single clock cycle. And overall, on average, um, this will run 4 times as fast. So um, because you can have 4 instructions going at the same time. So each individual instruction takes the same amount of time to complete. But on average, the instructions are completing 4 times as fast because we're basically having 4 instructions going at the same time here. Whereas in the way we talked about it before, we only had one instruction that had to go through each step individually before we started the second instruction. So we're getting 4 times the number of instructions through this process. So Yeah, so we would get 4 times the completion rate. Um, so on average, we finish 4 times the instructions in the same amount of time. So that process is called pipelining. And so it'll say it here. So a particular pattern of parallelism so prevalent in computer architecture that it has its own name, pipelining, which moves multiple operations through hardware units that each do a piece of the operation, right? Um, so one instruction still takes the same amount of time, but because all the pieces can be used at the same amount of time, on average, you get a lot more like computations done per time. Um, so basically, every processor is pipelined. This did not used to be the case. Like when I say it didn't used to be the case, I mean like we're talking like 1980, it wasn't the case. Um, 1990 already everything was pipelined. All right, performance via prediction. Um, so this is actually something that CPUs do as well. They use what they call branch prediction. And so basically, what they do is the hardware tries to predict, well, often they don't even predict, but they try to predict the result of the instruction before the instruction is done. And that way it can sort of work ahead. And, and so if you're processing something that says, if this is true, then we're going to do these steps. And if this is false, we're going to do these other steps, right? Well, if you assume that it's going to be true, you can get started on those steps, the ones that were the case for the true steps. Um, and then if you guessed correctly, then guess what? You're already done with some of the work. Um, and that saves you time. If you guessed wrong, well, okay, you wasted a little bit of time, but hopefully not too much. And so the hardware that does this is built into every CPU, and it's called branch prediction. And so there's what they call a prediction penalty. So like when the prediction is correct, you save time, and when the prediction is wrong, it costs time. And overall, it saves time because the branch prediction is good. Okay. A hierarchy of memories. So the entire way a computer is constructed um, involves a lot of different types of storage of a lot of different sizes, right? And that goes from even to the hard drives can kind of count, right? So like you could think of like this, like, okay, um, let's just think about the computer I'm using right now. Um, First of all, I have a NAS with, I think like something like 60 something, I'll say 60, I'll say, I don't know, 66 maybe terabytes of drives in it. Slow, right? It's slow, but it's very large. Then the computer that I'm typing on has a 4 terabyte, I said drives, I should say hard drives, like old school spinning disk hard drives. Then I have a 4 terabyte solid state drive in this computer that I'm typing on now. This is faster than the hard drive, right? Specifically, like how slow are these? Like maybe, well, I've got 3 of them, 4 of them running, something like that. Let's just say 200 megabytes per second. Okay. Now, and then I got a 4 terabyte drive in here. How fast is that? Well, that's much faster. I don't really know how fast this is. This is a made up number. I'm going to say 3,000 megabytes per second. Most solid state or a lot of solid state drives are faster than that now. They can be much faster than that now, but this is still fast compared to like a hard drive on my network. Um, but then these are just disk drives. We also have memory, right? So this computer has 128 gigabytes of RAM, and its RAM is, I believe, 400 gigabytes per second. Um, That's the computer RAM that's running while I'm running this, right? So that's much faster actually. But that's the RAM that we have here. But then on the CPU, we can look up M3 Max cache. So this is here. So on the M3 Max, we've got 32 megabytes, actually megabytes. Remember we were looking at the chart they showed us? So we have this many megabytes of RAM. And so let's see here. I don't know if this is RAM per core. This is performance cores. Let's just say, I don't know. So let's just say 32 of the L2 cache. So, oops. So we have less of it, but it's going to be even faster. I don't know the speed of it. And then finally, there's L1 cache, and you can see that it's small, like very small. And so I'll say 192. Okay. And maybe I don't have the numbers right, but you get the idea. So the idea is that the biggest storage I have is the slowest. And then the next biggest storage I have is faster. And then the next biggest storage I have is even faster. And these L2 cache and L1 cache built into the CPU are much faster, although I don't have the numbers. So yeah. So that's a memory hierarchy. Maybe we shouldn't have put the drives in there, but I think that helps make the point. So this hierarchy is like basically how all computers are kind of functioning, right? They've got different speeds and different amounts of memory in different locations. Okay. So the smallest is the fastest and the largest is the slowest. Okay. Dependability via redundancy. Um, Yeah, so computers need to be dependable, but they also, the way we can make them dependable is by making parts redundant. And this is done all over the place on computers, by the way. So one example of dependability via redundancy is this new NAS that I built for myself. It has four 24 terabyte drives in it, but only three of them are used. Basically, three capacity is the same as 3x drives. And the fourth drive is basically just for errors. And so so this is what do they call it? Brain farting on the term I want to use for this. But basically it's error correction code. And so the that's why it can't be capacity. It's just for blah, can't think of the word. Can't think of the word. But it's for redundancy. Redundancy. And fourth drive is for redundancy. So any drive can fail. Any one drive can fail, and I don't lose data. I just replace that drive. So that's reliability due to redundancy. So now, in order for my system to actually fail, two drives would have to fail at the exact same time, which can definitely happen. But with four drives, hopefully it's okay. And that's also how computer networks work. You want to have a lot of different connections, like between this computer, if I try to access, um, you know, a website that's in, I don't know, let's say England, right? So it's across an ocean and stuff. If you try to access a website in England, um, there's not one cable that could like be unplugged that would cause me to not be able to access that computer. Well, I mean, maybe there was, maybe, you unplugged the website that would do it. But, generally speaking, there's not just like one network cable that's carrying the signal. So if anyone fails, there's still other paths over the network to get to the same place. And so you need to have a lot of failures before things really become an issue. Okay. So redundancy is built in. Also, if you look up things like, maybe I can do this. Let's look up NVIDIA. What do I want to do? Let's look up a 4090, a 5090, no, 5070, 5060. I don't know, something. I want to look up the chips though, but I don't know the code for the chips, which is unfortunate because that's why we don't have Wikipedia here. Wikipedia. So show me the chips. Yeah. Nope. Where are they? Yeah, here we no. Yeah. So usually this is perfect. This is perfect. So these are chips in the current series of NVIDIA GPUs. And so look at these two here, the 5070 Ti and the 5080. And you can see that this says the GPU is GB203 and it says 300 and GB203 400. But if you look, they both are listed as having 45 billion transistors and the same die size. So how would they have the same number of transistors and be the same size? Well, they do it because they're the same chip. Okay. So these two are the exact same chip. The 5070 Ti and the 5080 are the same chip. But if you look at the processing power that they have, you can see like the CUDA cores, those are just for math computation. You'll see that this one is listed as 8,960. This is 10,752. So the bigger one has more, but it's not bigger, right? They're the same chip. So how come this has like more CUDA cores and this one has fewer? How come this has 280 tensor units and this has 336? How come this has 70 ray tracing cores and this has 84? Right? How come this has 8.75 megabytes of L1 cache and this has 10.5 megabytes of L1 cache? Well, what they've done here is they make these chips and then after the chips are made, they test them. And if the entire chip is working, it turns into a 5080. And if part of it is broken, then it turns into a 5070. And so they've made it out of a certain number of units, which I don't know if I see that anywhere here, but basically they've made this out of a certain number of like units that are repeated to make up the entire chip. And if some of them are broken, they can disable them. And so the one with the disabled parts becomes the cheaper GPU, and the one without the disabled parts becomes the more expensive GPU. And so you'll see that here for these two, the 5070 Ti and the 5080. And if you go down here, you'll also see it for the 5060 and the 5060 Ti, where um, they're listed as the same chip. And but one has fewer cores than the other one. So they just disable broken parts. And that way they don't have to throw away the entire chip if a small problem is on it. They can just make it a slower GPU. And so in fact they use that somehow because when I said here, like when I said, oh, if it's completely functioning, it's the bigger GPU, and if something's broken, it turns into the smaller GPU. That may or may not even be true because it's possible that this is not quite the entire GPU. On some of the GPUs that they make, the part, like the biggest part that they release is already like slightly lit, like slightly not slight. What do I want to say? Um, on some parts, some chips, uh, the capacity of the top end version, like the one that I'm highlighting now, the 5080, that might not be 100% of the chip. Like they might make some allowances to have some parts disabled even on the full version of the chip. So there's just redundancy built in, so that way, when something's wrong, they don't have to trash the whole thing, right? They can still sell all of them somehow. And so that's just a normal way now of doing that. They've done the same things with CPUs. Like back in the day, I don't know if they still do it, I would imagine, but if they make a 16 core CPU and a core is bad, well, they can still sell it as a 12 core CPU, right? So they don't, or they do that all the time. So it's part of the testing process. And before they ship it out, they just disable the parts that are broken. Okay. So, you can do some exercises here. Hierarchy of memories. What's that like? Is that like when a customer talks to a phone agent? No. Uh, House architect designs a house with 5 rooms, then designs room like closets, windows, and flooring. Um, okay. A college student rents an apartment closer to campus. Um, what? That's not really a hierarchy of memories. Oh, I guess it is. Okay. Like we said like fewer, like the smaller memories faster. So what they're saying here is if you talk to an agent, then you talk to the supervisor, right? So there's lots of phone agents and smaller number of supervisors, but the supervisors are like higher paid and they can do more, right? That's kind of like a hierarchy of memories. Um, Now here it says a college student rents an apartment closer to campus. Um, that's making the common case fast, right? Uh, you want to live close to school because you go to school most often, right? Or just get a house close to your work, right? That makes sense. Um, so it says a house architect designs a house with 5 rooms, then designs details like closets, windows, and flooring. I'm not sure that that's really abstraction. I guess it is the rooms are the abstraction. You're not designing all the details at once. First, okay, room is higher level abstraction. That's a kind of actually slightly awkward. Um, a sister is hanging clothes to dry. Her brother helps by hanging clothes simultaneously. So if they're both hanging clothes, that's parallel, right? They're both doing the same job. That's not pipelining. So remember the whole point of the pipelining when we talked about it was that there's these different tasks. And because they're different tasks, they use different hardware. So if you have 4 pieces of hardware, what we want to do is have one instruction at each level. And that way, um, all the hardware is busy all the time. That's pipelining. So here it says a brother is washing and drying dishes. His sister dries each dish immediately. So he's washing and she's drying. That's pipelining, right? So you can do things faster this way. If one person had to wash and dry, then it would be slow. But if one person washes and one person dries, then a dish can be being washed while another dish is being dried. And that's pipelining. Mom expects her son will be hungry, so she cooks dinner just in case. That's prediction. A drummer stick breaks, but he quickly grabs another one and continues playing the song. Right. So, you have more drumsticks than you need. So that's redundancy. Don't know why it didn't let me put it there. Okay. Below your program. So they're going to be talking about how you have application software like this web browser that runs on system software. That's the operating system. And then the operating system runs on the hardware. Okay. Compiler, program that translates high-level language. All right, let's see. Behind a car, simple items like steering wheel, gas pedal, and brake pedal are complex mechanical details. That's an abstraction. So, like when you turn the wheel of your car, you don't have to know like what the connection looks like, right? Like how does turning the wheel actually turn the wheels? You don't need to know those details. So they hide the details from you, right? Like when you press the gas pedal, like, well, how does that actually affect the engine? We don't need to know, right? In order to use it, you don't need to know. So they don't tell it to you. So the details are hidden, but the easy to understand gas pedal is presented to you. All right. The physical machinery that software runs on, of course, that's hardware. Software that manages the hardware resources on behalf of the other programs, that's the operating system. A program to play tic-tac-toe, that'd be an application. And the collection of software on a computer that provides services to application software. I guess that would be the system software. They're kind of saying that it doesn't have to be the operating system, I guess. But here they called it an operating system. Um, all right. We're going to be doing MIPS assembly language programming later on in this class. Um, And when you're writing assembly language programs, the instructions you're going to use are going to look something like this, like add AB. It won't actually be that. It'll be like add, it'll be more like, let's type one. It'll be something like this, add V0, A0, 1, or something like that. So this would say, add 1 to whatever is in the register A0 and store the result in V0. So the instructions look like this, but they're kind of just representing a simpler version here of that. And so when you're writing a program, you can write the program in machine language that's like zeros and ones. So when they were writing the very first programs for the very first computer, they got to write them in zeros and ones because that's all that exists. But that's hard. So they developed assembly language program which uses instructions like this add instruction or this add instruction. And that's a little bit easier to write. Like it's easier to look at something that says a add a comma b than it is to look at zeros and ones, right? So assembly language is easier to program in. And then at some point, though, that's still too hard, and that's why they invented programming languages like, C or C++ or Java, things like that, that are even simpler to understand. It can do more complicated things. So an assembler is basically like a compiler. The difference is a compiler is generally smart. Compiler is generally smart. It like you write a for loop and it has to take that for loop and say, okay, how like what instructions will actually make up a for loop, right? The compiler has to know that. However, when you're writing a program in assembly language using things like add a comma b, then in order to turn that into machine code, there's no thinking involved. Like add a comma b, there is an instruction, like the CPU knows how to add numbers, right? That matches up one to one with a CPU instruction. So with an assembly language program, the in an assembly language program, the instructions map up one to one with the CPU. And so the assembler just needs to convert what the user typed into an instruction. So, like the user typed in one line, you turn that into one CPU instruction. The user typed another line, you turn that into one CPU instruction. And it's always one to one. So the user types one line, and then that gets compiled into one machine instruction. That's a little bit different than a compiler, where, if you write a for loop or an if statement or something like that, Your CPU doesn't have an if statement built in. Your CPU doesn't have a for loop built in. Those are not like CPU instructions. So the compiler has to figure out what CPU instructions to use. But an assembler doesn't have to do that because it's all one-to-one. And so you can think of an assembler just as being a compiler, but just for assembly code. And they're simpler. All right. Assembly language, symbolic representation of machine instructions. We just talked about that. Machine language, a binary representation of machine instructions, right? Just zeros and ones. Is bit a binary digit? Yeah. Binary refers to 10 to the negative 1. Um, no. Com Computers use binary because binary is more powerful. No, they use binary because electricity, they want to they want to make a computer that just uses electricity on, electricity off, right? Two possible values. Um, Although binary's alphabet contains two letters, 0 and 1, the binary alphabet can represent as much information as the English alphabet's 26 letters. Um, let's see. The binary alphabet? Well, you cannot represent 26 letters out of, you know, just a 0 or a 1. But if you use multiple bits, then you can. So I don't know what they think here. I'm going to say true, and I'm going to assume that they wanted us to think that you could use multiple bits, but that might be wrong. Yeah. So they say it's okay. They say use more bits. Okay. The number 12 can be represented in binary as 1100. Okay. If a computer's memory location contains 00001100, then that location contains the number 12. Yes, but that's actually this is like yes, but thing. This is true unless this is like there's a thing called big Indian versus little Indian. That would mean that this might be 12, but also might not be 12. I'm gonna say true. Yeah. Um, oh, okay. That's not what they were getting at. They're saying just because this is 12, maybe it's not 12 in the specific context because maybe this wasn't even a number at all, man. Maybe this was code for a particular letter in the alphabet. Okay, sure. The following could be a machine language instruction. Why not? The following could be an assembly language instruction. No, assembly language is the one that says like add A, B like this. So an assembler translates the assembly language instructions like add A, B to machine language. Yeah, that's what it does. Okay. So this is an example. So this is kind of what I was talking about here. Like if you write something like this in C, like you said, what does this say? There's an integer called temp, and then this moves a particular something into a temp, and then it moves a number into another place in the array, and then it moves the temporary value to this place in the array, and they called that function swap. Um, and then that turns into assembly language code. And so when you compile it, most compilers, they go from the big language, the complicated high level language, into an assembly language as an intermediate step, where these are the instructions that the CPU is going to run. Um, so like there's an add instruction and load and store and store. So this is like moving around a couple of numbers. And then JR is jump return, which means we're returning from the function. So you have the high level code, which gets turned into some kind of assembly language code. And then the assembly language code gets turned into um, the machine instructions, which are apparently here. Okay. Yeah. So compiler, you write this, and then it gets compiled into this, and then it gets assembled from there. What's high level? This. What's C? High level. High level allows you to think more naturally, right? An advantage of high level language is to implement it in less time, right? It's faster to write a program in assembly, or sorry, in C or Java than it is in assembly language. Assembly language is going to take you longer to write a certain amount of code. The advantage of a high level language is that the program is, oh, it is independent of the machine. That's true, right? You can write a lot of code. Like I can write code for my Mac in a high level language, and I can run it on a Mac. I can go run it on a Windows PC. I can run it in Linux. I have to recompile it, but the basic code will be fine. So I can reuse that code. Right, a little bit more. This is more just basics of computer stuff. I don't even want to do too much of this. Let's just kind of go through it. Um, what would write data to memory? Not a keyboard. If you're writing data to memory, wait, what? They say memory a lot. Okay. Okay, this is I do not like this section here at all. So they're saying in the processor, they have a control unit, which is controlling what the data is doing, and then a data path where apparently that's where the data is going to go when we're processing instructions. Then we got memory where we can store stuff, and then we have input and output. All right. So you're writing data to memory. Um, I guess that would be output. They say no. These words are vague here. So the thing that performs computations must be the data path. And the control unit must send signals that determine the operation of the other components. And I would assume that the memory stores instructions and data. And then when we're writing data to memory, I tried to put output there and it said no. So I guess an input device feeds information into the computer. Okay. Oh, okay. I see what they're saying. So when you read input from the user, that needs to be written to memory. And when you output to like a display, you need to read from the memory so that you can take that data and output it to the display. I was kind of thinking about that backwards the way it was worded there. I was thinking um, like writing data to memory would be outputting because we're outputting from the computer to the memory was what I was thinking, but that's not how they're thinking of it. Okay. Um, they're talking about displays here. I'm going to skip it. Touch screens, whatever. A liquid crystal display works by having the liquid crystal generate different colors of light. No, you can read up there, but liquid crystals are going to block light, and then you have to shine light through them to get light. Um, a typical computer display is made up of hundreds of pixels. Um, at least hundreds. I mean, not hundreds, right? Millions. If you think about it, think about a computer that's 1920 by 1080. That's basically 2 megapixels. So, thinking about it, 1920, 1920 by 1080. That's roughly 2 megapixels. If you multiply those numbers, it'd be about 2 million. So not hundreds, but millions. An active matrix display is an LCD that uses a transistor to control whether light passes for each pixel. Okay. Um, each pixel typically involves 24 bits, 8 bits for each red, green, and blue. That's normal. Not the only way. There's 10-bit displays now that do 10 bits per pixel. A frame buffer stores the pixel values of the display. Yeah, so a buffer can be a storage location. And if you're storing a frame, think of like a frame of video. Those are the pixel values for the display. A touch screen combines the display with touch sensitive screen. Yes, that's what it is. It's a screen that you touch. Um, here's an iPhone XS. I guess that's probably like 10 years old now. I don't know, maybe more. Um, Smartphone, cool. Pictures, all right. An integrated circuit is often called a chip. They're not called CPUs because there's a lot of different chips. So a CPU could be called a chip, but so could like RAM. You could have a chip of RAM. Also, your video card has a chip in it, right? So any kind of computer circuit in a single package is going to be called a chip typically. So the CPU's chip physically occupies um, blank of an iPhone XS. So the chip was here in this picture, and that is, where is that over here? They, I don't see it in this picture. They left it out of this picture, so you can't really see how big it is, but this is going to be small. Depending on what kind of chip it is. This might be the size of a thumbnail, or it could be bigger if it's a bigger CPU. So they are a small fraction of the size of the phone. The iPhone XS Max contains how many chips? Um, I didn't count. Let's say 7. The A12 package has a chip containing blank large ARM processors. I don't know. For um, probably 5 based on the age. Fewer than 5. Okay, blah blah blah. Was it? It was not 2, was it? Ah, it lied. Okay. 2 identical large ARM processors. It also has 4 small ARM processors. I was thinking it had about, 6, but large was why it was only 2, because there's 2 big ones and 4 littler ones. A CPU is also known as a processor. All right. Um, so we sort of talked about this just a little bit when we were talking about memory hierarchies. So um, your DRAM is like the main RAM. So like this is what I have 128 gigabytes of on this computer. And then faster than RAM, but basically more expensive to make is SRAM, which we have not talked about previously, but it's just a different type of RAM. And cache is built into the CPU typically. It didn't always be that, it wasn't always that way, but cache is typically built into the CPU, and it's sort of a temporary storage on the CPU that keeps a copy of stuff that's in RAM so that it can be accessed faster. Now, just to show you, if I go back to Amazon here, since it's still open, if I type SRAM, uh, maybe we can't find any 32 megabytes, maybe that'll work. No, it doesn't, because there's a brand called SRAM. That's unfortunate. Let's try electronics. Really? We can't even buy any SRAM on here? It's disappointing. Um, okay, we are sort of failing here, but you can actually buy little boards of SRAM, and if you were making, you could make something like an Arduino, and you could actually buy a little SRAM board if you wanted some fast RAM to put on the Arduino. something like that. All right. Instruction set architecture. That's basically the way the processor works. Those are the instructions that the processor understands. And then there's something called an application binary interface, and that is how, like, basically the operating system has defined how to have a program in as a binary file. Like when you have an executable file, um, you have to follow the application binary interface in order for that program to work. That's why you can't run like a Microsoft Windows app on a Mac or vice versa. Um, Even if they had the same CPU, which they don't now, but they used to, even if they had the same CPU, you couldn't run a Windows program on Mac or a Mac program on Windows generally because they have a different application binary interface. So that's like an operating system thing, whereas the instruction set architecture is a built-in, like the definition of the CPU, like what instructions the CPU has and how they're defined. Okay. So an instruction set architecture enables machine language program to run on different hardware implementations. Yeah. So what that's about is you can define this, right? I said it's how the instructions are defined, how the CPU instructions are defined. That allows you to have, like, I can make my CPU for a particular instruction set architecture, and then you could make your CPU for the same instruction set architecture, and we should be able to run the same programs if we both followed the same instruction set. Um, maybe my CPU is fast and yours is slow, but maybe yours is low power or something like that. So um, the instruction set architecture allows multiple CPUs to be created that all support the same architecture. While different hardware implementations may run the same program, designers strive to keep the performance of new hardware the same as older implementations. No, I would say no. I think they normally want newer processors to be faster. Um, why did I say true here? It says, well, oh, I said the words I would say no, and then I checked false, or then I checked true. Um, they do not try to keep performance the same. They want to make performance better generally. Volatile versus non-volatile memory. Volatile is like when you turn the power off, what happens? So if you turn off the power on your computer, everything that was in RAM is gone. Okay, that's volatile. But if you turn off your computer, you keep what's on your hard drive, right? So that's non-volatile. Main memory could be called primary memory. Secondary memory, well, that could be like disks. Magnetic disk could be like a hard disk or other things. Flash memory, you're probably very familiar with at this point. See, what memory is used to hold programs and data while programs are running? That's RAM, which is the main memory. Um, Memory used to store programs and data between runs. That's what they called secondary memory up there, like disks. A form of memory that retains data only if the memory is receiving power. So if it needs power, it's volatile. Um, if it retains data in the absence of power, that's non-volatile. And then non-volatile semiconductor memory often uses secondary memory for personal mobile devices. Yeah. So what's a disk that you use a lot? That's going to be flash memory, right? Like you have a USB flash drive or something. And then the last one must be the magnetic disk, which is like hard drives and things. Okay. So, you can answer these last couple yourself here, and I'm going to call it a day. So, networking connectivity is the key part of modern computing devices. Sure. Ethernet is wide area network. No, Ethernet's usually local. Wireless networks are more common. Sure. What's volatile? Your RAM is volatile. What's the most expensive? Uh, RAM, right? RAM is expensive. Flash is cheaper and disks are cheaper than that. And what has the largest access time? The slowest are disks. Okay, now we're done. So I'm going to call it a day here, and I'll talk to you guys later. This is just to get up a video this week, and I'll talk to you guys in a bit.